Hello everyone, my name is Fernando. Today I would like to talk about the power of unentangled quantum proofs with non-negative amplitudes. This is joint work with Peivu. So let's start. What is quantum entanglement? A quantum entanglement is a form of quantum correlation that can be much stronger than classical correlations. Let's give some examples of that. So here we have two states. The one on the left is not entangled, whereas the one on the right is entangled. So a state that's not entangled is product, right? It admits a product form. So here we have the first vector tensored with the second one. Whereas here we have this state here, it cannot be expressed as a product of two vectors. So this is an entangled state. In the case of pure states, a state is entangled when it cannot be expressed as the product of two states. So here we have a very canonical example of an entangled state, an EPR pair. Very good. Whereas here we have something that's product. So it's not entangled, whereas here it's entangled. Very good. This is for pure states. And then when you move to mixed states, you need to be more careful. So now the definition of what it means to not be entangled is to be part of this set, and that's the set of separable states, which is going to be the convex hull of the tensor product of two rank 1 operators. So whenever we have a state in the separable state is a non-entangled state. But what is the meaning of now an entangled state? And an entangled state now is anything that's not separable in this definition. And you can already see that's already a more complicated description, right? Entangled means does not belong to this separable set. Very good. So this is in a nutshell what entanglement is, or at least bipartite entanglement. And entanglement is a very important resource in quantum information, computation, cryptography. It plays a central role in many areas, right? And if, for instance, if you want to go beyond classical computation, you may need to generate some amount of entanglement. Otherwise, a computation that generates little entanglement can oftentimes be simulated by a classical computer in an efficient way. So entanglement is an important resource for computation. Entanglement can be used to hide information, right? In quantum crypto protocols like quantum key distribution. It can be used for communication and teleportation, that we share some entangled states. It can also be used to protect a state against the environment, against noise, like quantum error correction, and so on. So entanglement really is a central notion, right? And despite its importance, now we know much more, but still we do not fully understand the implications and limitations of entanglement. It's a very rich phenomenon. So, and you'd like to better understand entanglement as folks in TCS. One way that we can do that is using the lens of complexity theory. Let's jump into complexity to try to better understand entanglement. And let's give a refresher to QMA. So there is a version of quantum NP that's called quantum Merlin-Arthur. And this model is going to be what to expect. So here we have some language or a promise problem. You have Arthur, that's a verifier. Arthur is given an instance X, right? And it's trying to decide whether this is a yes or no instance. But Arthur is polynomially bounded, right? So he may need some help, and Merlin comes and can give Arthur a quantum proof now, a quantum state with polynomially many qubits to help Arthur decide whether this is a yes or no instance. Okay, so that's the QMA class. Let's define it a little bit more formally. So Arthur is going to be a BQP, a polynomial time quantum verifier. In the yes case, there is a proof that makes Arthur accept the probability at least C. And in the no case, no matter which proof Arthur receives, he's going to accept with small probability S. So that's the completeness parameter, and S is the soundness. Very good. And an important parameter of the protocol is the gap between the completeness and the soundness. And as long as the gap is a constant, we say that this problem is in QMA. Okay. So that's a very natural version of quantum NP, the QMA class. And one can try to extend it, right? And one way of extending is to think that you have now not only one, but two Merlins, right? The two Merlins, they are going to provide two proofs, and we are going to assume that there is no entanglement between these two proofs. So there is, they will be in product form. Very good. So this defines a class that's called QMA2, right? Because now I have two Merlins. Let's again define it a little bit more formally. So Arthur is again a BQP verifier, polynomial machine. Now in the yes case, there is a product that two proofs, right, in product form that causes Arthur to accept with probability at least C. And in the no case, no matter which product state that Arthur receives, he accepts with probability at most S. And again, there is a gap, the difference between the completeness and the soundness parameter. And this needs to be at least a constant, okay, to be in QMA2. Very good. So that's a very natural class to define. And you may be asking, what are complexity bounds? How QMA2 is related to other classes? And that can directly see that if Arthur ignores one of the proofs, we get that QMA2 contains QMA, right? Sufficiently to ignore one of the proofs, and then you can focus on this one, and you have the power of QMA. That's a trivial bound. And on the other end, quantum proofs of polynomially many qubits, they admit classical descriptions of exponential size, and a non-deterministic exponential time machine can guess a classical description of those proofs, and then simulate the Arthur's protocol. Okay, and in this case, you can see that QMA2 is contained in an exp, non-deterministic exponential time. So this bound is also a trivial bound, right? And very good. So we gave two trivial bounds for QMA2. Very good. And other natural questions might be, if instead of having just two Merlins, let's say that you have K Merlins, many more Merlins, right? And that gives, and they are also not entangled, right? The proofs are not entangled. This gives rise to a class called QMAK, right? For K Merlins, right? And the natural question is, what is the relation with QMA2? And Harrow and Montanaro, they show that they are actually the same. QMAK is the same as QMA2. And what was very nice in this result is something that's called a product test. So in order to simulate K proofs using just two, they had a product test. It was already used before, but they proved its correctness. So in the product test, you receive two unentangled states, phi phi. And the idea is that those are going to be K-partite states that are K subsystems here. And the product test consists in applying a swap test here, another swap test here, and so on. Several swap tests. And they show that if the product test accepts with high probability, then one of the states that you have is indeed close to a product state. And if that's the case, you can carry on the QMAK protocol. So that's very nice. So with just two proofs, you can get K-partite product like this. Very good. That's a product test. And QMA2 is a class that has many connections to classical optimization problems like tensor optimization and so on, and also to problems in quantum information and so on. So let's see just one connection to illustrate why some folks also on the classical side, they care about QMA2. So one example is, if you look at Arthur can be described as a measurement, right? The yes and no part of the measurement. And the acceptance probability of the protocol, you're trying to maximize, you're trying to find a quantum state, which is a vector on the sphere, such that it maximizes probability, right? And if you think that this state has some coefficients alpha I, right, unknown coefficients, then this defines a degree for a polynomial on the sphere, right, on the unit sphere. Because each term here contributes a quadratic polynomial, but they are tensored, so we have a polynomial of degree 4. So the acceptance probability of QMA2 protocol is essentially a degree 4 polynomial. So here, notice that we use the same proofs, but this is without loss of generality, thanks to the results of Harrow and Montanaro. Okay, but very good. And there are many more connections, and if you're interested, you can take a look at Montanari's paper for several of them. And we have seen those trivial bounds, right? On one side, QMA is contained in QMA2, and QMA2 is contained in an exp. But can we do better, right? Is there anything non-trivial going on here that we can say? And unfortunately, we do not know. We do not know any bounds that are better than the trivial ones, at least in general. That's surprising, right? Given the connections, the interest that there is in this class. But QMA2 or some versions of it, they have shown some sparks of power, right? That you're going to describe. So one very nice result was this beer and tap result. There they have two unentangled proofs of logarithmically number of qubits, and they show that this class already contains NP, right? Very interesting, right? In the classical case, if you have two proofs of logarithmic size, you can do essentially nothing, right? You can brute force and guess them, right? And find them by brute force. But in the quantum case, two quantum proofs of logarithmically many qubits, you can already capture an NP. The catch here is that there is this gap, 1 over poly, that we're going to discuss later. It's a very cute and protocol that they had. And if you combine their result with a result of Merritt and Waters that tell us that QMA with just one logarithmic size proof equals BQP, then there is a conditional separation, because under BQP being different than NP, we have that having one or two proofs in this setting is already different. And why is that? Because here by Beer and Tap, this contains NP, and by Merritt and Waters, this is equal to BQP. So if they are different, those two classes, they are also different. So this is a nice conditional separation. And if you want to get a constant gap, right, a better gap, Aronson, using only square root of n proofs of logarithmic size, they could put NP inside this class. So instead of requiring n or something larger, if only square root of n proofs of logarithmic size, they can already get a gap that's constant. So that's also very interesting, gives some sparks that an entanglement may be powerful, but you need to be careful, right? If you're trying to understand, if you try to scale up those results to QMA2, you need to be careful. The gap in Beer and Tap protocol, for instance, is going to hurt us, right? It scales naively as 1 over exponentially small, 1 over xpn. So then the gap is so tiny that we cannot put an exp inside QMA2 in this way, right? So it's not conclusive for QMA2. Beer and Tap result, this naively. And if you can try to scale up Aronson's protocol, you might need too many proofs, right, of polynomial size. And we cannot have, can only have polynomial many. So you cannot put an exp inside QMA2 directly using this protocol. So for QMA2, unfortunately, these two results, they do not tell us that much. Unfortunately, they are non-conclusive. And on the other side, in trying to get better upper bounds, in general, we also have nothing, right? There were some attempts using powerful SDP-based hierarchies, SDP-based techniques, but unfortunately, no better upper bound than the next. Clever nets and even some a variety of definite theorems, but in the general case, they couldn't improve beyond the next. But in some restricted case, when you restrict Archer, the verification protocol, then you can indeed get something better, but unfortunately, not in the general case. So there is no better upper bound currently than an exp. So, okay, we have this class QMA2 that is connected to many things, captures entanglement in some ways, and you'd like to better understand it, but it evades the complexity part, the algorithms part. So what can we do to better understand it? One thing that we can do is to bring an extra assumption, right? Now let's suppose that we have these two margins, but the twist that we're going to add here is that the proofs, the amplitudes are non-negative, are real numbers that are non-negative, let's say in the computational basis, right? So the amplitudes are non-negative. So we have two unentangled proofs of non-negative amplitudes. that's going to be the model that we're going to consider. Okay, so this is going to give rise to this class that we're going to call QMA plus 2, and the plus is because of the non-negative amplitudes proof, and it's defined as in QMA2, right? In the yes case, there are two unentangled proofs of non-negative amplitude, causing Archer to accept probability at least C, and in the null case, no matter which two proofs of non-negative amplitude you give Archer, Archer accepts with probability at most S. And we also have a gap, the completeness minus soundness, and that needs to be at least a constant, let's say. Okay, that's going to be our QMA plus 2. Very good. And this is essentially a non-negative amplitudes version of QMA2. And why we defined it this way? What was the goal behind this definition? So we want a class to capture many of the structural things that we had in QMA2, right? We want to have a class that's similar to QMA2, but at the same time, we want extra structure to be able to say more, to be able to improve things, to improve our understanding. So that's why we consider this QMA plus 2 to have this balance, right? Very good. And the non-negative amplitudes will allow us to design global protocols, robust protocols that have constant gap for a variety of problems. So here we are going to have small set expansion, unit games, more general forms of constraint satisfaction problems. Very good. And when you have a problem that you do not fully understand, then it's nice to bring some more structured, seemingly hard problems like unit games or small set expansion. So here we have the best form of hardness that you can have for some problems, NP hardness. That's the gold standard. But if you cannot establish NP hardness, it might be worth trying to establish UG hardness, the silver standard, borrowing from Dor. Or if not, then you can bring an even more structured problem, like small set expansion. That's a weaker standard, but may also give some indication of hardness. Okay, so we have these three standards. So they may be helpful. They are used a lot in the theory of hardness of approximation to have some idea of hardness. Very good. So we're going to give protocols for these problems. And these protocols, they are going to crucially rely on expansion properties, robustness properties of the instance together with the non-negative amplitudes assumption. And together, they are going to give us protocols, global protocols of constant gap. It's very good. Here we do not have a lot of time, so we need to focus on a few aspects. So one of the simplest of the protocols is the small set expansion, and it already captures a lot of the ideas. I think it's a very clean protocol. So I'm going to focus our attention more on the small set expansion protocol, and later I'm going to say a few things about the more general CSPs. Okay, it's going to be the goal. Now let's recall what is the small set expansion problem. And in the small set expansion problem, the input is a deregular graph. And in the yes case, there is a small, at most delta n vertices, a small set that is not expanding. When you look at the fraction of edges that that's across the cut, that's close to zero. Okay, there is a small non-expanding set. Very good. Whereas in the null case, no matter which small set that you consider, most of the edges are leaving this set. Okay, so it's a bit counterintuitive with the name, right? Small set expansion. So in the yes case, there is a non-expanding set, whereas in the null case, every small set is expanding. Okay, in the yes case, there is a non-expanding set. Very good. So that's the small set expansion problem. And you can already see that the definition is very robust, right? So in the yes case, we have almost no edges crossing, and in the no case, we have almost all of them crossing. There is already a very good notion of robustness built into the problem. It's a very well-structured problem. And what would be a quantum proof that you would expect? A very natural quantum proof would be to have a uniform superposition, in the yes case, of the non-expanding set. So the Merlins, they can give proofs of this form, right? And that just a uniform superposition over the set. And we are going to need a simple fact about the regular graphs that the adjacency matrix of a irregular graph can be written as a sum of permutation matrices. So let's see an example. If you have something like this, a cycle, it can be written as two cycles, one clockwise and another one counterclockwise. So that's a decomposition. So any irregular graph can be decomposed in this way, a sum of permutation matrices. And that's nice because those are unitaries, right? Valid quantum operations. Now let's define the protocol. The protocol will receive many copies of the psi. It's going to check that they are close to each other. It's going to take one random permutation, apply to psi, and it's going to compare this application with psi itself. Does it stay similar or does it change a lot? And in the case that the set is non-expanding, when you apply random permutation, the mass is moved only inside the set S. It doesn't go across. So you're just moving mass around inside S. So we should have that psi and the permuted version, they are roughly the same. They're roughly same state, so we can detect that. And in the null case, most of the edges, they are across. Right? So when you apply a random permutation here, most of the mass is going to leave S and go to the complement. Okay? And when that happens, the support of PR times psi is going to be disjoint from the support of psi. And then you're going to get an approximate orthogonality. The support of these two states are roughly disjoint. And we can also detect that. This can also be checked. Very good. So that's the protocol. On top of that, we also need to check sparsity. Okay. But if you believe that you can check sparsity, then we have achieved that the small set expansion is contained in a version of QMA2 with of non-negative amplitudes with logarithmic size proofs. And the gap is going to be a constant gap. So that's first theorem here. And let's detail a little bit more what is this sparsity test. And in the sparsity test, we are given some psi, and we would like to ensure that the psi is close to a uniform superposition over a small set S, a set that has at most delta n elements as before. So you want to have psi being close to a state like this. And what would be a very natural test to enforce sparsity, right? One thing that you can ask is for the uniform superposition over the set and also the complement of the set, right? So if you have the set and the complement, you can check for orthogonality, right? You can compute the inner product between the set and its complement, and you should see something that's zero because the supports are disjoint, or at least they should be disjoint. And here you also introduce this all ones, the uniform superposition over everything, and you check correlation of psi with the uniform superposition and also the complement with the uniform superposition. And we require these two quantities to thread up to one. Very good. And let's see why this is good. So if the test passes, then what you get is that psi is indeed close to a subset state, to a uniform superposition over a small set. Here, we take their inner product, and that's going to be close to zero, right? And now the non-negative amplitude is going to be used in a crucial way, right? Because if you have non-negative amplitudes and you see that the inner product is roughly zero, this tells us that the support of these two states, they are disjoint, right? Because we cannot have cancellation. So it means that the support of psi is here, and the support of its complement, this other state, is here, is disjoint. So that's very nice. And the correlation with the uniform superposition is at most this much by Cauchy-Schwarz, and is at most this much. And if you get this as roughly an equality, it means that psi needs to be flat, needs to be uniform over its support. Okay, because it's saturating the Cauchy-Schwarz inequality, and similarly here, if psi is saturated, if this states psi complement saturates this inequality, it needs to be flat here. So we get that subset states in the end, which is what we wanted, and we are done. The protocol works nicely. Very good. So we do not have time to cover the unique aims protocol. And let me just mention a little bit what happens with the more general forms of constraint satisfaction problems. So at some point, we need to scale up the protocols that we developed from NP to all the way to NXP. And the main theorem that we show there is that NXP is contained in QMA plus 2, right? And since this is also QMA plus 2, like QMA 2 is contained in the NXP, we have a characterization of QMA plus 2. And the main challenge in this scaling up is that the R2 protocol needs to be inefficient. It still needs to be a BQP machine, right? So you need to be more careful when you scale up the protocol. What are the ingredients here? Let's just give a summary of the ingredients that we use. We are going to start with a suitable PCP for an exp. Okay, you're going to massage to adjust this PCP so that it's going to have some nice regularity property. And for this, you're going to use expanders. And we also want the PCP to be very explicit. So typically, the PCP has one-sided explicitness, and you want some form of two-sided explicitness that I'm not going to describe. Very good. And after you have that naturally gives us an associated CSP, and you design a protocol in QMA plus 2 for this associated CSP that appears there. So those are the ingredients, right, for that theorem. Okay, that's all that I want to say, or at least you can say for now. And you may be asking, okay, it was nice. We have this definition of QMA plus 2. We can characterize it. We have just shown that this happens, and that it happens with completeness and soundness that are constants, and the gap is a constant. So we have this nice thing. But what is the connection with QMA2, right? The initial class that you want to understand. And something that there is a very curious connection that occurred to us later, is that there is a very nice connection. In fact, QMA2 can be characterized in terms of non-negative amplitudes as a version of QMA plus 2 with a completeness and soundness gap that are constants, and the gap here is sufficiently large. So this result was established with a small constant gap. This requires a larger constant gap. Okay, but then if the gap of QMA plus 2 is sufficiently large, it equals QMA 2. That's very good. And trivially, we have this containment. So these two classes are somehow related in this way. Okay. And the gap here is a small constant, the gap here is going to be a larger constant, and all the completeness soundness parameters are constants. Okay, so that's a very curious relationship between these classes. It's not hard to prove. And another similarity that QMA plus 2 has with QMA 2 is that this unentanglement assumption is very powerful, right? We can also do the product test because of this unentanglement assumption with QMA plus 2. And the product test implies non-trivial gap amplification to some extent, a nice extent. So what the product test for QMA plus 2 tell us is that if you start with some version of the class that the completeness soundness gap can be 1 over poly, the product test can amplify this as a corollary of it to completeness that's exponentially close to 1, right? Super good completeness, and the soundness that's a constant soundness. Okay, so can do a quite non-trivial form of gap amplification, QMA plus 2. And if you had QMA 2, right? Harrow and Montanari, they show that there is a form of parallel / sequential repetition that would allow us to somehow power the completeness and power the soundness, right? Without leaving the class, as long as you're not powering too much. So here this also holds for QMA 2, the general one. The completeness is very close to 1. So even if you power it, I don't know, by sufficient large constant or even much more, this remains close to 1, whereas this constant goes exponentially fast to 0, right? So you're increasing the gap as we apply this lemma. So very good. For QMA2, there is these two pieces of the gap amplification that we know that they work, and QMA2 has very strong gap amplification. Then, in our case, the first part of the gap amplification, this quite non-trivial part, works, but we need a way of reducing the sounds, right? And that we should do not know. That's needed. If you want to obtain that QMA plus 2 equals to QMA2, we need to be able to improve the sounds. Okay, so that's as far as today it seems to be old. Okay, so very good. So that's relation. Now let's conclude. So I think this QMA plus 2 class raises many questions. I think it's a very intriguing and interesting object to study, right? And it has this striking connection with the QMA2 class itself. And very quickly, we can mention two things, right? So potentially can have a win-win, hopefully win-win condition in terms of how to improve our understanding of QMA2 or unentangled. In the first scenario, let's say that suppose that we have that QMA2 equals to QMA plus 2. In this case, can we prove this using amplification, right? Using some form of gap amplification, more careful one. Or should we open the protocols and design protocols that achieve better gap in one shot? Do not know. Those are very natural questions, right? And in a scenario 2, let's suppose that QMA2 is strictly smaller than QMA plus 2. And in this case, since those classes, they share many similarities, can you focus on the pieces that they are different, right? And try to understand, I do not know if you understand well enough where they differ. Can you capitalize on that? Can you design better algorithms? If you understand very well how these two classes different, can you give better upper bounds on QMA2 itself? So I think studying QMA plus 2 may be interesting regardless of the scenario, right? At least in my opinion, seems a very curious object. And our initial motivation was to better understand entanglement and so on. And what can we develop along the way? Can you sharpen the tools that we have? And what is the improved understanding about entanglement that you can acquire in this exploration? So I'll stop here. Thank you very much for your attention. And that's all that I want to say. Thank you.